I'll give you a background in the meanwhile. The thing is that I'm doing a research for my PhD for making a blockchain solution for pharmaceutical industry. Now, what do you call? While making the solution for them, I found that there is one major problem in the sense of security of the network. Basically, because right now everything will work nicely in the solution which I'm working, but this same solution is vulnerable about 10 to 15 years from now. Basically, because by the time the quantum computers will be here, and the whole thing that we make right now will be rendered useless in that period of time. So, instead of being happy about having created a solution, I want to make a future-proof solution so that it does not break down when quantum computers are on the horizon. So that is what is the whole intent all about. So I made a discovery, and the solution works, and that's why I want to share it with all of you. And the same problem will be there in your organizations also. You may be, I'm not sure whether you're even aware of the problem which I'm talking about today. So it is to make you aware so that you can start working on it right away.
That helps, Partha. But would you also give a little bit of a brief of what is the current solution before you start with the...
Of course.
Yeah, okay. Sounds good. Thank you.
No.
In the meanwhile, Partha, I'm again asking you the same question. Do you have any plans to restart the LLM?
Yeah, I do have a plan, but the thing is that I am extremely busy right now. I want to do it in a concentrated way so that I don't start and then I have to break out in the middle. Like I have told you guys, I have got a project from USA,
yes,
which is very taxing, and I put a lot of money in that, so I can't afford to fail in that.
Absolutely.
So that is the reason why I'm not able to do it. And in the meanwhile, I have to take care of my 2 PhDs. And today I took some 1 hour out basically because this is part of my work which is ongoing. And I thought, let me share it out with you guys. I will definitely restart the LLM class and complete it also. Just give me a few weeks. I will do that.
Absolutely, Partha. Whenever, like, even if you do it after a year, we'll be here. Like,
I'll
be here to join.
It will not take a year. Don't worry about that.
Okay.
It will not take a year.
With year will be too late. Then we have to go for an advance.
that is correct. Yeah. But appreciate it, Partha. Thank you.
I really appreciate Partha. Yeah. So the things that we have discussed so far, I'm just seeing how well we can start move forward with the SLM. Especially, I'm seeing in my domain that there is a need of an SLM coming in. So that is where I was eager to know from you with your LLM course that you also gone through with ISA, I believe. So we thought, okay, that really helps us.
So the thing is that I have all the material which is required to be discussed because as a part of the ISC course we have to make a solution. Okay, we cannot just make a presentation project and all that. So the ISC course we have to make a solution and we have to demonstrate the solution. So I've done that. I made SLM and I have shown it to them and they were very appreciative about that. So I have the entire thing with me. So I will just do that. Maybe just give you about few weeks. That's about it. Not more than that.
Sure. Thanks, Partha. Thank you.
And lastly, before we begin, Partha, just in case if you are also thinking about some course on agentic AI, we'll be also interested in that.
Agentic AI is something like first of all, agentic AI is now become a part of LLM actually. So when we will discuss the LLM program, which I will restart with you guys, we will end with how we can extend LLMs to agentic AI. So that's it. That anyway, you will get a full mathematical background of that.
Great, that is wonderful. Thank you.
Yeah. So let's start. I don't think anyone else will join. So let's start. So this what do you call experiment which I did? This is about pharma supply chain, like I told you. The pharma supply chain. Basically, see, the thing is that in pharma world, what is happening is that we have the manufacturers and we have the retailers. Then also we have many other players. Like apart from manufacturers in India, we also have importers. A lot of medicines are imported. Then after the manufacturers, the medicines go to the retailer, the distributors, and from the distributors it goes to the retailers, and from the retailers it goes to the consumers or hospitals and things like that. So there's a lot of movement of the medicines. Now in these movements, what happens is that there are many what you call players who are mischievous, and they introduce fake medicines into the network, and that is why this what do you call, when you're actually buying medicines, you're not very sure whether it's a genuine medicine you're buying or it is not a genuine medicine that you're buying. This is a very big problem. At least 10% of the medicine which is in circulation in India is fake. Okay, and so unless you buy your medicines from a what do you call very reputed retailer, then you are always in a constant danger that you may be subjected to counterfeit medicines. It's a very big problem. So now what is happening in the current scenario is that there is a system, there is a supply chain system which works, but it is entirely database based. So we are tracking, the government is tracking the movement of medicines, so everything is happening on a database. And you know that in a database, what happens is that what do you call? I can alter records, right? It is not a very difficult thing. I can alter records, and I can and that is very difficult to catch. So so that is the reason why my research is that we should adopt blockchain for this, because blockchain will ensure that what do you call, the records what we have are immutable and they are not alterable, and that is going to be more secure. Now, as a technology part, that is already proven, and the many big players like IBM or some people in China, etc., they have made solutions which are working. But all the solutions what we have in this regard, they are on a small scale. There are no solutions which is there on a very big, large scale. Like, you know, if I want the solution at the level of a national level of India or national level of China, there is no solution in the world so far. So that is why, though the people appreciate that blockchain is the future for such kind of a problem, but then we don't have a solution. So my effort is basically to ensure that how can I make a scalable blockchain solution which can be implemented on a nationwide scale, like India or a big country like China, or even what do you call, places like Europe and America and things like that. So right now we do not have a solution for that. Now, while making the solution, now the thing is that you understand the blockchain works on a cryptographic backbone. So when you're making a transaction on the blockchain, the transactions are encrypted, and that's how they enter into the chain, and then they are securely backed, and then what do you call, only the people who authorize, they can extract the information from that and check it out, and other people cannot even do that. Now, there are two kind of blockchains which you may be aware of. One is a permission blockchain, and one is a permissionless blockchain. Permission blockchain, I have implementation like Hyperledger Fabric, which IBM has created. Now, in permission blockchain, what happens is that we give permissions to certain people to be able to transact on the blockchain, and only those people are authorized to do any kind of transactions on the blockchain. Even to read something, they have to be having permissions for that. Now, this is very, very secure, and this is what is preferred, especially when it comes to what do you call, a closed network like we will have in a pharma supply chain. However, we are also having non-permission blockchains, like, you know, you are making this what do you call, cryptocurrency transactions, etc. You're buying, selling cryptocurrency. These are all non-permission blockchain. Anyone can get into it, and anyone can make a transaction, and anyone can view what is happening and things like that. So that's what we have now. See, the thing is that whether it's permissioned or whether it's non-permissioned, but the thing is they all rely on a cryptographic backbone. That is that the transactions or the authenticity, everything has to be encrypted, and only then you can come into the blockchain. Now, forget about blockchain. Even when you're doing any transactions on your financial systems or even on your healthcare systems, etc., we are all using encryption technologies. Like you must be experiencing that you have this what do you call you use this RSA tokens. Now, in many applications, you have these one-time passwords which come to you, and then you feel secure. Okay, fine. I have a two-factor authentication, and that's why I'm giving a one-time password which is known only to me, and I will not share it with anybody, and then I can go ahead. Right now, this entire system which we are utilizing, it works on a technology called RSA tokens. RSA stands for reversed Shamir and Alderman. They are the three people who invented the RSA algorithm, and we are all using this RSA token. Now, RSA token, what happens in RSA token is that it's basically a mathematical problem which is being solved. Like, what is happening is we take internally we take two numbers. Let's say I take two numbers P and Q, and these two numbers are very large numbers, and they are relatively prime to each other. So individually they may not be prime, but they are relatively prime in the sense that these two numbers they do not share any common multiple between them. So I take these two numbers and I multiply them, and I get a very large number like n, and this is what I will share. Now, after I share this number is available to everybody in the world. But what you will do is that you will utilize it for your purpose. Now, basically, the purpose is that you will have two keys with you. One is a public key and one is a private key. All right. One is a private key. Now, the private key remains with you, and you do not share it with anybody, and you make the public key available in the world. So what happens is that when you encrypt anything, you will encrypt with your private key, and it goes out in the world. Only the people who have your public key can utilize the public key, and then they can decrypt it. Right now, so this makes your transaction secure. But the thing is that if everyone has a public key, then anyone can decrypt your message. So what I will do is that, supposing I am user one, I have a public key. So this is PU1, and I have a private key which is PR1, and you are a second person who I'm interacting with. So you have a public key PU2, and you have a private key PR2. So what I will do is that I will take your public key, I will encrypt with your public key. So this is PU2, and then further I will encrypt this whole stuff with my private key. So I will encrypt with my private key. So PR1. So this will give a encrypted message. Now to decrypt this, what I have to do is that I have to first of all utilize my public key, which everybody will be having. So I utilize my public key, which everybody has. But then you will be having your private key. So when you decrypt, you will decrypt with your private key. So this is PR2. So in this way, what happens is that only you are able to decrypt my message, and nobody else in the world can decrypt my message. So this is a very powerful technology. Now the thing is that the whole technology depends on the fact that this n being a very large number, I'm showing it to you. But then to be able to get my private key, you have to factorize this n so that you can get the P and Q. Right. Now, this problem that to factorize and to get back my P and Q is a very difficult problem. It is mathematically impossible. Like, what do you call it? We require a computer, even with a computer with having about 30,000 or 40,000 processors. And if I try to find out the P and Q for a given number n, it will take about 2 billion years. So it is nearly impossible to break, and that is the reason why we are all utilizing this RSA technology for encrypting our messages, and we are all safe at this point of time. Yes, Aditi.
Partha, I might be simplifying this a little bit, but if P and Q are both not relatively prime to each other, for example 2 and 3, then n becomes 6. So factorizing 6 becomes very easy, right? Because it will always be 2 and 3.
No, but the thing is that I am not going to choose a number like 2 and 3 when I'm going to make my encryption, because these will be very large numbers.
Correct.
Very large numbers, like what do you call? Normally, we started with taking these numbers as 512 bits long, and now we are encrypting using 4096 bits and all this kind of stuff. So we are talking about very, very large numbers, right?
Sure, but don't you like, my question is that if these are not like these are relatively prime to each other, then the problem becomes even more difficult, is it not?
No, what do you call, the whole algorithm stands on the fact that these have to be relatively prime. Relatively, like you said, 2 into 3, right? Now 2 into 3, both 2 and 3 are prime numbers. Now the problem is that to find a prime number is very difficult, right? It is not a very easy problem to find a prime number, especially when the number becomes very large. So what we do is that we take very large numbers, let's say 5, 2, 1, 4, 5, 7, 6. So I take such a number, and I will not take an even number. I will take some odd number only. Now, then I will find a number Q, which will be relatively prime. That is, it doesn't have any common factor with this particular number. Then they become relatively prime. They're not prime numbers individually, but they're relatively prime.
Okay. I forgot the part they are not prime numbers individually. Okay, understood. Thank you. Yeah.
Okay. Now, so RSA is a very safe technology as of now. There's no problem. But the thing is that this RSA technology, I told you, it is very difficult to break. But the thing is, now we have the quantum computers. Now in quantum computing, what happens is that we have a specific algorithm called Shor's algorithm. Okay. Shor's algorithm. Now using Shor's algorithm, what is possible is that I can break a RSA token in a polynomial time. That is the same problem which I'm going to take 2 billion years to solve. I can solve it in about 2 hours, 2.5 hours, right? And this poses a very big challenge, because what do you call, being able to break it in 2 hours means that my entire crypto system is going to be compromised. Anyone can take a RSA token and they can break it using using a quantum computer, right? So first of all, are you getting appreciation of what the problem is all about? Yes or no?
Partially, Partha.
Okay, see, you are able to understand that the RSA algorithm is keeping you secure at this point of time. All your transactions are secure. No one can break it, right? But if instead of using a classical computer like we are all doing right now, if someone sits with a quantum computer and he can break the RSA token within a few hours, now don't you think your information will get exposed?
Right. Yes, definitely.
So if that is going to be the case, then are you secure in the quantum age?
Not in the future, yes.
Yeah. The only thing right now we're not worried is because this quantum computer doesn't exist. what we have done is that we have shown that we can use Shor's algorithm to break small numbers like 15 bits numbers or 16 bits numbers. Right now we are able to do that because we have quantum computers of that scale. And we are building quantum computers of a bigger scale as the time is passing. So in about 10-15 years, we'll have quantum computers which will be able to deal with very large numbers like we are using in the RSA tokens right now. So the thing is that at this point of time, you are very secure. You're not bothered. But then 10-15 years from now, your information will be not secure because someone can use a quantum computer and they can break your information. Yes, Aditi.
Partha, this is true not only for pharmaceutical, for entire banking systems. This that like
Everything.
Yeah. Okay.
Everything. Financial systems, healthcare systems, everywhere. Because everywhere we use the same technology, RSA tokens. Right. Okay, so do you get the essence of the problem now? Yes or no?
Yes.
Okay. So now let's move forward. So what we have to do about it? So this is what is the reality. When we have the quantum computers, the entire public key system which we are using right now will become broken. But now you may say that, okay, fine, I'm not going to be worried now. You're talking about something anyway, which is 10 to 15 years back down in the future. So why are you making us scared at this point of time? So I will explain to you a concept which is available in which the hackers are using called harvest now, decrypt later. I will explain this to you. Then you will become aware of the problem in reality. So now to mitigate this, what is happening is that the NIST, this is the National Standardization Institute, they have made a technology called ML-DSA. ML-DSA basically stands for Module Lattice Digital Signature Agency. Now, this ML-DSA is not breakable by quantum computers. Okay, so this is something which has been developed already. Now I experimented with ML-DSA, a specific version of ML-DSA, which is known as the ML-DSA 65. This was my scope of my experiment. Now ML-DSA 65 is not breakable by the quantum computers, and at the same point of time, it is able. We can use it for our current computing requirements. But then what do you call, just because I can this doesn't break doesn't mean that this is usable. Simply because if it is not possible to conduct the transactions in a reasonable period of time using the new technology, then the new technology is useless. Like, I cannot wait for a one-time password infinitely or maybe even 10-15 minutes and then proceed. It has to be happening at the same speed what is happening today. So that was my scope of my experiment. That is, if I use ML-DSA, am I able to perform the transaction with the same efficiency like I'm able to do with the current technology, which is RSA, or there's another parallel technology called UCC, Universal. I'm forgetting the full form of this. I will tell you. I'll remember. So these are parallel. Both are breakable by quantum computers. So that is what is the whole thing about. So if in case this technology is workable, but is it feasible to use it in the practical scenario today? That is what I'm going to tell you about. Okay. Now, so what I set up is that I set up a situation where I have a manufacturer in a blockchain and I have a distributor and I have a pharmacy, and these are all connected in the Hyperledger Fabric, which is a permissioned blockchain. The thing is that the transactions must happen, and transactions must happen, and they should be permissioned, and they should be what do you call secured by cryptography, and elliptic curve. ECC stands for elliptic curve digital signature algorithm. Okay. Now, right now, the cryptography what I use is this ECDSA. So I set up this whole thing where I had the same blockchain, and I kept the same current ECDSA as the encryption technology, and I was running my blockchain. Now, but I know that this ECDSA is vulnerable to quantum computers. So, so what the thing was that um, since this is vulnerable, so I had to check if I replace this ECDSA with a ML-DSA, then whether I will have the same efficiency in the quantum computing as I was having with the classical computers. So that is what is the whole thing about. So now, okay, now let's look at the problems. What people are doing is that right now quantum computers don't exist. So what they're doing is they are tracking all your information, like healthcare data, financial data, pharmaceutical data, whatever. They're tracking everything and they're storing it. And they know they cannot break it because the algorithm is secure. But then they're waiting for about 15 years from now when the quantum computer will be available, and then they will take out your information and they will break all the information and they will get the internals of the information. At that point of time, they will start utilizing all the information what they have broken and got the raw data, and they will start monetizing it. So things like, what do you call, you have your healthcare records. It may seem like today you have your healthcare records, but yes, Aditi.
I'm sorry, maybe I raised my hand too early. I was asking what kind of data are they harvesting, but I think you are talking about that already. Sorry.
Yeah. So any kind of data, it can be like, you may say that your financial data. Now, supposing it is even for a common man, your financial data or your healthcare data, it can be exploited by the people, even if they know about it about 15 years down the line, right? But what about the same information if it is from some key political figure or something like some important dignitary and things like that? They become much more valuable, right? So that is what is the whole danger all about. So if we do not change our cryptographic layer today, then we may think that we are safe because now nobody is able to break our information, but the same information will be exploited the moment the quantum computer becomes available. So do you get the problem, what I'm talking about? Do you have any questions or do you have any comments on that?
I have one comment. Partha, this must be the same when the cryptography must change from, let's say, manual at some point to when computers came, right? So they must have faced the same kind of problem at that time.
Yes, even historically, they must have faced the same kind of issue.
Right.
Right. So that's why the moment we are aware of a problem, we should take corrective actions. And right now, so the thing is that right now it is not time to relax and think that we are secure, because we are not secure actually. And there is somebody who is just collecting information and waiting for the right time to start exploiting it. Right now, the only point that remains right now is, do I have a technology which is suitable without disrupting my current operations, so that I can utilize it and also secure my future. So that is where my experiment starts in, and what do you call? I use the ML-DSA, the module lattice digital signature architecture, and I will show you my experiment results, so that which prove that they are as efficient as the current ECDSA, and at the same point of time making it future secure. Okay, so this is standard. This is coming from the National Institute of Standardization and Testing. So this is the technology called ML-DSA, module lattice digital signature architecture, and it uses this MLWE module learning with error. I will not get into the mathematical part of it, but that will form a totally different discussion. So maybe one day if you're interested, and right now maybe it is a little early to discuss that because it may overwhelm you. So, but anyway, you can know the basic things about it. Yes, Aditi.
Without going into the details, the people who have worked on the standard are fairly sure that this algorithm will this cryptographic method will work with the quantum computers.
Yes, that is proven.
Okay.
That is proven. So we have now there are many standards on this. I will show you the different standards which exist. I made a note of that. What do you call? So you can see here, these are the different standards which exist. Can you see the screen properly, or should I make it larger?
This is fine. I'm able to view.
Yeah, a little larger would be better, but our full screen of this.
Okay, let me make it full screen. Yeah, full screen, I am little afraid my computer doesn't work properly. Okay. Is it better?
That's okay, yeah.
So here we are here right now, ECDSA. This is what we are doing. You can see that we use this relatively small key and what do you call, small public key and a private key, but then we have more powerful technologies which use a larger key, and though you must be very sure that you're using what do you call, SHA and all this kind of stuff. So these basically form here, they're category 1. So ML-DSA falls in category 3. So it is fairly secure, but it is not the highest form of security. So the highest form of security right now that we have is ML-DSA 87. This is what the key here is very large. I will tell you why the key size matters. What do you call? But the ML-DSA falls somewhere in middle, and it is fairly secure. So all these technologies, what you're seeing here, ML-DSA 44, 65, 87, these are all quantum secure. They cannot be broken by quantum computers. Okay, and these have all been proven, and they have been approved by NIST. Okay.
And these might have different applications also. For example, military use or some other high security.
Yeah, like ML-DSA 87, this is basically used for military use.
Okay.
And they're very high form of security, and this is not possible to use in commercial applications. With the two things, one is that if the algorithm becomes very what do you call, complex, it will take more time to execute, and if it takes more time to execute, then commercial applications may not be viable because it will keep hanging, and you'll keep waiting as a user for the computations to complete. That is number one. Second thing is that if the keys become large, if I encrypt my data with a large key, even the encrypted message will become very large. The encrypted message becoming very large has a problem that it has to travel over the network, right? So I have to have more transactions, which will not more transactions. I will have bigger payloads, which will have to travel on the internet, which increases the cost of transactions, which may not be commercially viable for regular transactions. So this is the basic problem. So I need to find a middle path. Apart from the another problem also lies that if the messages become very large, then I will require more storage, right? After encrypting, if my messages become very large, my storage requirement also will increase. So that also adds to the cost. Now, all of this is not free because everything I'm going to be adding up, and then I will say that now your transaction cost is so and so. So a simple thing like a UPI transaction, which is being offered free right now, may not be able to be provided free. We may have to we may have to make a charge for that. So this is the problem, right? Any questions? Any observations?
So,
Okay.
Partha, one question. So, similar to RSA, which we are identifying, okay, 15 years down the line, this can break. Was there any study done on ML-DSA that when this can be broken?
No, what do you call this? So the thing is that there are scientists who are working on that. It is right now, I don't have the data regarding whether they have found anything regarding that. The simple reason is that right now the quantum computers itself does not exist, right? So as far as quantum computing is concerned, this is secure, that has been proven. But what after quantum computers? What kind of computers we will have? We do not know that future. So we may get some other kind of computers where this may be also compromised. That possibility lies, but right now that future itself is not clear to us. Right
Okay.
now, our future is the quantum computers. Right. Okay. So
But I also have one observation that as the time will pass, even the storage and like the data storage cost and everything will also go down, right? That is what we have seen historically.
yeah, it will go down. Scale always brings things down. But still, what do you call? See, the thing is that back in 1995, I was making a MRP2 system in Thailand, and we started the bare bone computer with only a disk operating system, that is DOS, nothing else on that. And we were making a MRP solution which should be installed in factories across Asia and Australia. Now, right that time we were writing the whole programs in C, and we were so conscious that our program, all the machines on which our programs would work would have only 256 KB of RAM. So we had to be very calculative when we were writing our programs as to how much memory they will utilize. So, so that was a constraint under which we had prepared the entire MRP2 solution. That this program should work on a 256 KB computer. But then, right now, when you are programming, you don't even think about what is the memory my program will utilize, right? You forget about calculating. You just declare variables as and where you want. If you face a difficulty in writing a program, you just declare a global variable. All of these things were very big challenges when we used to write programs in the past. Yes, so now this is democratized programming. That is, now many people are able to write. See, earlier we had to have specialists who had to write programs for specialized operations and applications. But right now that is not the case. Anyone can write. But then not that it produces the best programs, but it works. That is what the reality is. Would you agree with me?
Yes, yeah.
Okay. Okay. So the basic, I will show you from my paper what is the setup which I made. I have the setup on my machine. I'm using the same machine where from where I'm talking to you. So this was the setup. I used my Apple Mac and I used ARM64 CPU and all this kind of stuff. So this is what is the environment. So, and I did not get a data set which is from the pharmaceutical industry. Instead, I used a retail database which is publicly available, and I just slightly modified the data set so that it represents a pharmaceutical supply chain. So that was the whole effort. And then I tried at different levels of load. So I tried with 50 TPS, 100 TPS, and so on. So you can see here, I tried with different levels of load, and I got my results. So now the basic results is that what do you call, the whole thing works. First of all, just like it was working with ECDSA, it works with ML-DSA also. Then entire thing works, and this is what is important here. Now you see that as I'm increasing my as I'm increasing my transactions per second, the throughput of ML-DSA actually improved, and it surpassed that of the ECDSA. So this is something very encouraging. Okay, and equally encouraging is the fact that the latency what I'm getting on the ML-DSA as the load is increasing is much lesser as compared to that of ECDSA. So on both fronts, ML-DSA is performing much better. But then comes the most crucial question. That is, most crucial question: does it occupy more amount of space storage? Now, this is where the finding was very surprising. I will give the exact figures. Just 1 minute. I will give the exact figures. One minute. Okay, another important thing here, you can notice here, that is, let me see if I can make it larger. Yeah, now view, fit, zoom, fit to width. I think now you can see better, right?
Yes.
Yeah. So you can see that, see, when I'm performing such high, performing transactions at such high rates, in ECDSA, the number of errors are very high as the load is increasing. Okay, it cannot handle so many number of simultaneous transactions. But the same thing on ML-DSA is the errors are very less. This is another advantage which I'm getting from ML-DSA while this is becoming all more secure. Now comes the through what you call payload part. Now see here, you can see here that in ML-DSA, I'm not actually using more amount of space. It's almost comparable. So I'm not actually using much extra amount of storage, though the key size is much bigger as compared to ECDSA. Right. So this should give you the confidence that what do you call you can apply ML-DSA 65 to your security layer, and you will be not only quantum secure for the future, but also you will have we will have no extra overhead of utilizing this technology. Did you get the essence of my experiment?
Wow, this is very surprising, Partha.
Yeah.
And quite encouraging, yeah.
Yeah. Now the thing is that what I did was like this. What do you call? I changed the transaction signing signing layer with ML-DSA security. But then what we also have is that for the transactions to take place, we have to have the certification authority. I did not change that because what I did was that I ran the same experiment once with ECDSA and once with ML-DSA, and I did a comparison between the two. So as a result, I had to have some things. I could not change something. So the CA I did not change. I kept it as ECDSA, and also the TLS I kept it as ECDSA only. But what do you call? This is something which I can replace very easily. Now the next stage of experimentation will be, supposing I replace the CA and TLS also, then will the numbers remain the same like I have got right now? And only if I replace these two layers also, then I become completely secure. Right now, though my transactions may be secure, but if someone can break my certificate, then they can get hang of they can introduce a false certificate and they can get hang of all my transactions. So that is the problem in this particular architecture which I have set up. But that is my next step. I will replace these two also, and I will make a completely secure transaction framework. In fact, that is the book I'm writing right now. So if you want implementation of that, you can read my book and you can implement. It will give you step by step with complete code, everything what has to be done in that regard. Okay. Yes, Aditi.
Partha, I have two questions. So, in any experiment, we do like repeatability, right? So, are you like, do we need some more experiments to be done on this before it can be like actually implemented with, let's say, more amount of data or different key size or whatever?
Yes. See, the thing is, one weakness in my experiment is that I set up the whole thing and I only ran it once. Now this is basically because I had a paucity of time. I did not have enough time in my hand right now. But actually, what I should have done is that. So I have proved that in a single run, these are comparable and while giving much more higher amount of security. That is something which I have proved. But then the thing is that all these throughput statistics which I showed you, which I got them from only one run. So I should have actually run it about 15-20 times. And after that, I should have found the mean and everything, standard deviation of that. And I should have also reported to you what is the confidence interval. Like, I'm saying you will have you will have the transaction rate at so and so, and you will have the error rate at so and so, and all that kind of stuff. But then, what is the confidence with which you can say that? So I should have reported those statistics also. So that is something which is the work the next person can take up and complete.
Amazing. And second question was that how, like, right now quantum computers are not there. So is the solution still implementable at this stage, or do we have to wait?
That is the whole point I'm telling you. You should immediately implement it.
Immediately implement, yeah.
So that though you don't have quantum computers today and you are not able to see any breakdown in your services, but then if you don't make this change, what will happen is that there are some people who are sitting and capturing information, and they will exploit it in the future.
Right. Really, really amazing, Partha. I really hope that this goes to lens and you get to make a lot of money out of this solution.
Yeah. Okay. Deva, you have any questions? Did you find it useful?
Yes, Partha. I think, right now in my company, it is not, because I don't deal with any financial or the supply chain thing. But yes, we need to look at how a communication framework will be secured anyway. So that's something that we still have, since we also work with some of the defense contracts and stuff. So obviously this will be useful. So my question is, today with the existing infrastructure that we have, so I should be able to change to move to ML-DSA, right? So easily I should be able to do with the existing infrastructure itself.
That is exactly what I have proven. I have removed the ECDSA and replaced with ML-DSA, and everything works seamlessly.
Okay.
And within the same cost range. Yeah, that was also important.
Yes.
Yeah.
Yes. Correct.
Also, like on a different note, question, Partha, if we have to start because I have zero knowledge of quantum computing, so if I have to start, do you have any suggestions where to start?
Quantum computing. See, the thing is that I did an amazing program from IIT Madras. It started from the very basics, like from the ABC of quantum computing, right from the basic mathematics, the basic linear algebra, and then making the gates, and then moving from there on to quantum machine learning and things like that. So it's an amazing program. So you can just inquire with IIT Madras, and I would highly recommend that program for anyone.
Is it at a very technical level, like on implementation?
Yeah, it's very technical. That much I must tell you.
Okay.
Very highly technical. Very mathematical oriented and things like that. That is the problem.
Okay, but it's a good information anyway. Yeah, thank you.
Yeah. Okay, guys. So that's all I have to tell you. I thank you both for joining in. And I hope you will join in the future also for other things. And I will start the LLM program very soon. I promise you that.
Thanks a lot, Partha. Thanks for sharing this. It is really, really amazing of you to share this information with us.
Okay.
Thank you.
Okay, guys. Good night.
Yeah.
Bye.
Good night and bye.